This session will be chaired by Professor Alok Chakraborty. He is the former director of Variable Energy Cyclotron Center. First, he will be greeted by our student, Payal, and one young officer, Ruchi. Please do the honor. Sir, hand over to you.
It's all right. I think, shall we wait for a few minutes because the hall is still by and large empty. Well, okay. Welcome to the afternoon post-lunch session. And the first speaker is Dr. Jürgen Schuckraft from CERN. Dr. Schuckraft has been the former ALICE chairman, was the former ALICE spokesperson for almost, I think, 18 years. And during this time, he has worked out many international collaborations and played a key role in PMD installation, which is spearheaded by VCC, and the Bionan, which was spearheaded by SNP in the ALICE experiment. And of course, he is a very well-known experimentalist and the recipient of Niels Bohr Institute Medal of Honor. And well, in this campus, he is very well known to many of us. And welcome, and just begin.
Thank you very much. Thank you very much. How does it work? Yeah, it's on. And this one as well? Yeah. Okay, thank you also very much for the welcome gift, which is particularly appropriate given the high setting of the air conditioners. I'm grateful for the scarf. Now, given the historical context of this workshop, the exactly 160th anniversary of one of India's most famous most famous poet, and the approximate 75th anniversary of one of his illustrious scientists, I thought I will also give a talk with a with a historical background. But I will not speak about the history of a person, but about the history of a thing called ALICE, which is of course an experiment at the CERN LHC, which for the last over 30 years had Bikash as one of its main promoters, the one who participated from the beginning and who made the strong Indian participation in the experiment possible. Now, depending on the audience, I thought to say a few words about CERN. Are there any philosophers left in the audience which don't know CERN? Yes, so I will quickly make a few words about CERN. So what is CERN? CERN is standing for, in English, the European Organization for Nuclear Research. Essentially, it's the world's largest fundamental research center for particle physics. It's located half in France, half in Switzerland. And it is actually no longer true to its name. The E in CERN used to be European. The C actually used to be Conseil, Council. Because by now it's an international organization, not only from European member states, but it has 23 member states, including Israel, which is not European in the narrow sense. And it has 10 associated member states, of which the biggest one actually is India, which joined in 2017, and also here, Professor Bikash Sinha was one of the drivers and catalysts of this participation of India at CERN. CERN is a fairly reasonable sized budget, about the size of a typical mid-sized research university, not a big university, MBA, or Cambridge has a much bigger budget, with about $1 billion per year, and it has staff of about 2,500. Now, its mission is essentially to promote basic research in both particle and also nuclear physics. That's where the N in the name comes from. Essentially to study matter, what the universe is made of, and forces, what keeps it together. And the more philosophical version of this question is, but equally true, why is there something, at least something massive, rather than nothing, at least nothing other than light? Something is not an obvious answer to this question. That's one of the questions we are asking at CERN. And the way we do it is not by doing research at CERN with CERN staff ourselves, but by providing facilities, essentially accelerators and infrastructures to outside users. So CERN does not make any research itself, it provides facilities for others. And who are these others? Essentially, these are the particle and nuclear physicists of the world. By now, CERN has about 12,000 scientists. That's much larger than 1/2 of all high-energy physicists. And they come not only from the member states, a bit more than half, but almost 1/2, about 1,000, do come from either associate member states, observers, or non-member states altogether. And here you see the number of Indians that was in 2020. About 200, the biggest associate member community comes from India, and the biggest community actually by nation comes from the United States, with almost 2,000. That's the biggest user community at CERN. Now, these users are organized around experiments and collaborations. These experiments and collaborations range from small, from a few tens, to very, very large, a few thousands of scientists. And it's these users, these collaborations, which propose, which design, which build, and which operate their detector. And they're also funded via their funding agencies, so it gives a little help, particularly for the infrastructure. But people come with their ideas, and with their instruments, and with their money. And they have free access then to the data and to the site. And what's very important, these collaborations are administratively and scientifically completely independent from CERN. Of course, they are reviewed by peer committees, but they are not told what to do. And down there you see two of the last generation of big experiments and collaborations, which ran in the last 10 years of the last century. LEP, the Large Energy Positron Collider, the Delphi experiment, and the L3 experiment. Of course, you will later see this very same magnet again in others. Now, amongst the smaller experiments, at least in the 90s or the late 80s, were the heavy ion experiments. That's the experiment in physics we are doing with heavy ions, looking for the quark plasma. And here you see one of those, so-called WA98 experiment. And the reason I have picked that is, of course, evident, because this was the experiment where the first group from the VECC participated at the time with a very simple detector, essentially plastic sheets, and with electronics and cameras which they borrowed from another experiment. But they did an excellent job because they discovered something at the SPS which has been a mainstay of heavy ion physics ever since, namely the flow. You have heard much about flow in Barbara's talks and in many of the other talks. And I think one of the first, or maybe the first experiments who did actually find the flow was this experiment with the detector which was provided by ECC. Actually, its importance was not really appreciated at the time. This flow came to fruitful fruition only 10 years later at the relativistic heavy ion collider. And finally, this is now the Alice experiment. You see again the magnet which we inherited from the L3 experiment as part of the Alice collaboration. Now before, what is ALICE? In one word, it's really the most, by some measures at least, the most complex, biggest detector ever built for nuclear physics research. It was it at the time, and I think still today it is. Maybe other techniques are more massive, but definitely not in terms of electronics and channels as complex as the ALICE experiment. And our mission, and I will not speak more about the physics, you heard Federico, you heard Barbara talk about it, but our mission essentially is to recreate and then study the primordial matter of the universe, and there in particular see how composite objects, how nuclei which make the stars, the planets, and which make everything we see, how this emerged out of structureless soup of structureless constituents, something which is non-trivial and which we are still trying to understand. It goes under the name of hadronization, or the hadronization phase transition. Now it took many hundreds of scientists and engineers about 20 years to design and build the experiment. And then, since then, it takes literally thousands of people to run it and to analyze the data. And this will take another 20 years. Now, before going into any detail into this first part, this is the subject of my talk, the 20 years which we took to design and build the experiment, I want to add another dimension of CERN. After all, this is not only a conference about science. In the fact that CERN is actually a rather particular laboratory which was founded less than 10 years after the end of the Second World War in Europe. It is an international treaty organization like actually the WHO, like UNESCO. So it's an organization between governments governed by a treaty. So it's an extraterritorial organization. Of course, the main reason was to make fundamental research, essentially to pool the resources of the European countries which were destroyed largely during the Second World War, to pool their resources and be able to do something which none of them could do individually. But that's not the reason actually CERN was built and funded. I think we had very good scientific arguments to build it, but that would have not been enough. The real reason why the countries came together was both economy and politics. In terms of economy, one wanted to create a focal point for scientists and engineers in Europe which would be competitive in the scientific environment, and to stop the brain drain which happened before, during, and also shortly after the Second World War, that the best people just went at that point usually to the United States. And in order to stop the brain drain, one had to build a focal point where they could do things which are adequate to their intellectual capabilities in Europe. And the second equally important reason was politics. This was really 10 years after the end of the, or less than 10 years after the end of the Second World War. And in order to rebuild trust between the European countries, one tried to do that on neutral grounds in terms of science, in order to start collaboration again between these countries. Now, CERN indeed was an enormous success. Today, in terms of research, it is the biggest and the most successful center for high energy physics, with several Nobel Prize winning results, both people at CERN or who were doing work about what CERN is researching. And more than half, I think much more than half of the world particle physicists actually spend part of their research life at CERN. In terms of economy, it is an incubator in terms of many technologies which have been developed at CERN, some of them more or less exotic. The most well-known is definitely the World Wide Web, which was actually invented at CERN. And the influence of the World Wide Web, I think, can be compared arguably with the development of the steam engine in terms of the effect it has on the economy and on the culture since its invention. And not only did it stop, it actually reversed the exodus of physicists from Europe. I showed you that CERN is now the biggest American lab for high energy physics. And finally, in terms of politics, I think it is one of the most successful and effective institutions. Many other European institutions like European Space Agency, the European Molecular Biology Organization, have been modeled roughly towards the model of CERN, but none identical to CERN, because the scientific, the political and the economical environment which existed in 1954 did not exist 10 years later. If we would have not a CERN today, we couldn't recreate it. We would not get the money, and we certainly would not get the organizational and scientific independence. So we were lucky to be at the right people at the right time and make this unique proposition. The future of CERN, I think, is clear, at least for the near term. It is no longer European, it is global. And in particular with the LHC, the latest accelerator, even larger projects which are planned some 20, 30 years from now, can no longer be done even on a European or Western basis. It really needs participation from all the world. Politically, this has become more fraught, also with the latest developments of war in special operations, let's call it, in some parts of the world, with war in Europe, which now also stresses really the trust which has been built between scientists working together. And of course, in terms of economy, there's no way to tell what will be the future benefits of continuing this adventure. Okay, but now let's come to the subject of my talk, namely the ALICE experiment, which is one of the 4 experiments at the LHC. CMS, Atlas, and LHCb run with light ions, protons. But for 4 weeks every year, the Large Hadron Collider becomes a collider of large hadrons, of net nuclei. And that is where ALICE, but actually by now also all of the other experiments look into this physics of the strongly coupled quark plasma. Look at the primordial soup of the early universe. Now, the experiments at LHC are all big. You see here the Atlas experiment is about as high as building 4T, about 5 floors. They are heavy, actually. They are very heavy. Okay. So they are, the magnet of the ALICE experiment is about as heavy as the Eiffel Tower, and they took a very, very long time to build, 20 years. And you can see how long that is on the time scale of a human. Now, how long that really is, I want to illustrate by comparing the time scale of the LHC experiments with the time scale of previous generation of collider experiments. The mother of all collider experiments is the UA1 experiment, which ran in the late 70s and 80s. That was the experiment of Carlo Rubbia. It was proposed and designed within 1 year. It was constructed within 3 years. It found the W's and Z's and got a Nobel Prize after 7 years. And after a bit more than 12 years, the experiment was over, from the first proposal till the last data tape. That was long, but already at LAB, that's the next generation, it took 20 years. Much longer to design. There was a little bit of dedicated R&D, much longer to construct, and about a comparable time to run. But even Delphi was over after 20 years. Now, the first 20 years of ALICE just saw the detector being built. We didn't start physics before the time previous generations were already being dismantled. And what in particular stands out is that we had a very, very long time. The design was more complex, but we had a very, very long time to detector R&D, to invent new detectors. And this was actually crucial, not only for the ALICE experiment, but actually for all of the LHC detectors to tackle the challenge of LHC. Now, the LHC started actually already in the mid-80s. It was discussed in the mid-80s. Even 2 years before heavy ion physics had the first fixed target beams at both the SPS and the AGS in Brookhaven and CERN. And already 1 year later, we hardly had the first ion beams. Actually, it was light ions. I think it was Carlo Rubbia who said, why don't we put heavy ions into the LHC? This was typical Rubbia, just saying something which turned out to be a very good idea, but nobody had really looked whether it's possible, whether it's useful. And so we spent the next 2-3 years, while Rick was starting to build this experiment. We spent the next 2-3 years to see whether actually it would make sense to build a heavy ion detector for the LHC. And that was done for a workshop. Again, we physicists, we like to have workshops because it's always a good idea to A, see the people, and B, see a nice place. This one was in Aachen. And the conclusion indeed was that heavy ions at the LHC should be interesting, and more importantly, a detector. This was not evident at the beginning. A detector, a general purpose detector, could actually be built. This was at a time when only special purpose detector had ever been built for heavy ion physics. So, with this positive judgment, we went on about 32 years ago at the end of 1990 to have our first, what would later have been called an ALICE meeting. It was not, we didn't have the name yet. But we met for the first time and said, how can we go about building this detector? It started fairly modest, with some 60 people or so. It started very, very optimistic. We met in 90 and we thought maybe 2 years later we could already start occupying the experimental space. But we had a plan B. Even if physics operation was foreseen for 1998, that was very optimistic. We had a plan B, should this slip, we just stretch the schedule. And that's what we then essentially did for the next 20 years, stretch the schedule. Now, the next step was then to formalize that, and that was done with what is called an expression of interest. And that was shown again in the first LHC-specific conference in a little village close to Geneva. Some of you might know it for the water which it produces, Evian. We looked at different options. Can you reuse a lab experiment? Can you use a PP experiment, or do we want a dedicated experiment? And at the end, actually, we used all three. The dedicated experiment became ALICE. Both Atlas CMS and even LHCb didn't make heavy ion physics, and we actually reused a part of a lab detector named the magnet. Now note that BECC was one of the founding members at the first expression of interest. We didn't have a name yet. So BCASH, since more than 30 years, was actually at the crucial member and the catalyst of the ALICE experiment right from the first day. Evian is also remembered, at least by me, by another more unfortunate happening, a very sad happening. I don't know whether any of you probably the older ones do remember Prince Mahat, I think it's called Mahapotra, who was from the previous generation leader of the L3 group. He died at the meeting in Evian, I think of a heart attack. This was unfortunate, but it did lay the ground for the LHC experiments. Now, I'll show you here now how the ALICE design developed. It started off essentially with a pencil drawing on some, not quite napkin, but on some logarithmic paper.